In this video, we're going to go through an example looking at partial pressures and mole fractions and how we can convert between, say, a given composition in percentage by mass into mole fractions and use that to calculate partial pressures. So we're going to be looking at a gas mixture here called trimix that's used by scuba divers. It's a mixture of helium, nitrogen, and oxygen. And you need the right percentage, and specifically the partial pressure of oxygen, to be able to safely breathe underwater. If these percentages are off, you will not have a good time. And so this is one specific mixture that you can use, and we're going to use this example here. So it's 11.7% helium, 56.2% nitrogen, and 32.1% oxygen, and this is by mass, so not by mole fraction. We're going to calculate what are the mole fractions of each component, and then if we are given a total pressure, once we know the mole fraction, we can find what's the partial pressure of O2. So these are given as percentages, so and by mass. So what we can imagine is that we have 100 grams of this gas. Doesn't matter if that's how much we actually have. We're going to assume 100 grams of this gas, which means we'll have 11.7 grams of helium, 56.2 grams of nitrogen, and 32.1 grams of oxygen. Now, what we want to find is the mole fraction. So in this 100-gram sample, we need to know how many moles do we have of each component and what's the total number of moles. So we need to convert these grams into moles. So let's go ahead and use the molar masses. So 4 grams of helium per 1 mole of helium, which gives us a total of 2.92 moles of helium. 56.2 grams of nitrogen will divide by 28 grams of nitrogen per mole. Again, this is N2, so we need, remember, to multiply the atomic weight by 2, and that gives us a total of 2.01 moles of N2. So we can see there's a lot more mole, even though the fraction, the percent mass of helium is quite low, the number of moles is a lot higher than you'd expect because it's so light. The density is very low. And then for oxygen, we're going to divide by 32 grams of O2 per mole. I'm leaving off some significant figures so you could do this a little bit more accurately. And we get, that gives us 1 mole of O2. 2 within significant figures here. Okay, so we know our moles of each of these, so what's our total number of moles? Well, we just add these together. 2.92 plus 2.01 plus 1.00 moles, which gives us a total number of moles of 5.93. Okay, so our goal is to find the mole fraction, so we know the moles of each component, and just as a reminder, the definition of mole fraction is the number of moles of that component divided by n total. So we know each of those. So we can find the mole fraction of helium, which is going to be a lot higher in terms of percentage than its mass fraction, or mass percentage. So we have 2.92 moles of helium divided by 5.93 moles total, which gives us a mole fraction of 0.492. We can repeat that for nitrogen. We get 2.01 divided by 5.93. And as you may have noticed, the mole fractions are unitless because the moles cancel on both the numerator and denominator. Let me give myself some space here. So that is equal to 0.339. And then the mole fraction of O2, which we'll need to do the last part of the question, is equal to 1 mole divided by 5.93, which, if you put into your calculator, gives you 0.169 moles. Sorry, not moles. There's no units on that. Or you could express these as percentages by mole, by number of atoms or molecules. There's 49.2% helium, 33.9% nitrogen, and 16.9% oxygen. So you can see it's a little bit different when you're thinking about the numbers of particles versus the weight. So, and that's, again, just like we talked in the last video, the densities are very different for these gases. So let's go ahead and calculate the partial pressure of oxygen then. So we were given the total pressure is equal to 1.5 atmospheres. So that means the partial pressure of oxygen will be our mole fraction, 0.169, times 1.5 atmospheres. This one I haven't calculated in advance, but we can do that one real quick. 0.169 times 1.5 is 0.25 for, we can round that to 0.25 atmospheres. So of that 1.5 atmospheres total, only a quarter of an atmosphere of that pressure is due to the oxygen. A lot of it's going to be due to the helium because it has a significantly higher mole fraction. All right, so that's some examples of how we can use partial pressures and mole fractions to look at mixtures of gases. We'll do some more, again, do more examples in class. But that concludes this section on partial pressures. And then our last set of videos for Chapter 5, we'll be looking at the kinetic molecular theory of gases and real gases.